Hey, I'm Rick, and I work for a company called Mechanical Rock, based in Perth. We do a lot of work with serverless technologies, and so I thought I would do this talk to help anyone save themselves a bit of heartache when it comes to using Appsync and DynamoDB and how to use them more efficiently. So why use Appsync or DynamoDB? Appsync is AWS's GraphQL service, and it allows for defining a schema as well as the data and queries that can be performed on that data and any relationships. With GraphQL, you can request as much or as little data as required in a query. You get real-time updates with one line of code. You can use VTL templates to talk to core AWS services such as DynamoDB, RDS, Elasticsearch, Lambda, or any HTTP endpoint. And unlike REST, with GraphQL, you can request multiple related entities at the same time, which strangely enough is one of the core value propositions of DynamoDB. DynamoDB is AWS's cloud-native NoSQL database. It's serverless, scalable, offers great performance, and it fits in really well with the serverless ecosystem because of its stateless HTTP connection model, which makes it really great to use with things like Lambda and Appsync. So in this picture, you can see the differences between single table and multi-table design. I would like to credit Andrew Brown for the image in the slide, and his Twitter link can be found in the slides with this deck. So DynamoDB tables should never have been called tables. Instead, they should be thought of as databases. And that's because the access patterns that DynamoDB tables expose can be thought of as tables themselves, in that those are the different querying patterns that you can use. When you model data in DynamoDB, you really want to think upfront about the access patterns that your application will need. And that's because you don't want to lock yourself into an inflexible schema design that leads you down the road of having to perform a table migration. So focusing on access patterns up front means that you can design for flexibility in your querying. And you'll be able to query your application in as many different ways as required. Multi-table design is great for newcomers, and that's because it's more forgiving. You get more indexes, which means more access patterns, and you get a dedicated stream for each table, which means you get eventually consistent updates. You can use it for streaming data into other data stores if you wanted to. So why would you choose single table design then? Well, if you look at the previous picture, you've got the really buff dog that kind of illustrates single table design, and that's because single table design is actually much more powerful than multi-table design. And that's because using single table design, you can group related data into the same table and then use a single query to access all of that data at the same time. And the way you can do this is by reusing partition keys and prefixing the sort key with an item type. An example of the query we would use a simple query we would use to access all of the data in the same table would be the one you see in the slide over here, where you access a single partition based on an ID value. And unlike REST and RDS, you don't have to make multiple requests or create queries that join several tables together. With Appsync and DynamoDB, you use one query and you get all of the related data to a single item. So to demonstrate a broad spectrum of data modeling practices, we will assume that we are building an application. Let's call our application Regia. This is an application that is about managing projects. It helps managers to keep track of the current state of all projects being worked on. It allows for employees to understand the priority of the work that needs to be completed. Employees can get assigned to tasks and to projects. Managers can easily find stats and metrics about any projects they are interested in. And to build this application, we're going to build it serverlessly so we can focus on solving the problem that delivers value to the business instead of managing technology and infrastructure. We will use Appsync and DynamoDB so that we can build an application that is responsive in terms of performance. Our users will be able to receive real-time updates, and the application will have the flexibility to request as little or as much information as is required. This example is great because it will allow us to illustrate the best parts of both approaches when it comes to DynamoDB table design. And to demonstrate those concepts, we will be using a mixture of GraphQL queries and mutations and Appsync VTL request and response mapping templates to provide some insight into the API layer and the subsequent request that gets made to the data store. So to provide an overview of the different entities that we will have in Regia, you can see here that users can belong to many projects and projects can have many users. Projects are also made up of many tasks, and a user can be assigned to one or many tasks. And here we can see that projects also have metrics that build up over time. To provide a 50,000-foot overview of our very basic architecture at this point in time, you can see that we have our React Apollo application, which makes requests to the Appsync API, which then makes a API call to DynamoDB table using ETL templates. So to start things off, we'll create a project for our application. And to do this, we will use a DynamoDB put item API. Using the Appsync util object, we can generate a v4 style random UUID for the ID field. And using the Appsync DynamoDB utils, we're ensuring that all the attributes for our project are mapped to the correct DynamoDB types for the API call. And here you can also see that we duplicate the ID field and place it in its own dedicated field that is not the partition key. And so this is very important when you're modeling data with Appsync and DynamoDB. And that's to do with the client that is most commonly used with Appsync, which is called Apollo. Apollo has a normalized client-side cache that it uses to automatically update cached query responses when mutation responses or subscription updates are received. Apollo looks specifically for the ID field and uses it to find the correct object to update in the normalized cache. And the benefits of this are that it's less work for the developer. You don't have to worry about app state management, which means less bugs. And it also means it's really simple to implement real-time updates. So you really want to make sure that each item has that ID attribute and that you use generic names for partition and sort keys. And this will allow you to do things like model one-to-many relationships where the partition key is not always the ID value for the item. And so a prime example of this is this create task mutation we have here, where again we use the util, the auto ID, to create a ID for the task. We also prefix that ID with the item type. And so here you can see that this mapping template is a lot similar to the previous one we used. But the key difference to know here is that we're actually using the project ID as the item partition key, and we're putting the item ID into the sort key, as well as the attribute values. So this will help us do things like find only the tasks relating to a particular project. If we had that requirement to make that query, we would use the task item prefix on the ID to make that query. So here's an example of, after inserting two tasks, what our table might look like. We have our project ID as the partition key. We then have our detail item, which has the details about the project. And then we have our two task items under that same project partition key. And so this is what a query to get all of the tasks relating to a specific project would look like. You use the begins with condition expression with the task ID prefix to check for items that start with task and have a particular project ID. So in the previous slide, you saw how we could fetch all the tasks for a specific project without getting any details about the project. But this means you're only getting back a part of the picture. If you wanted to use the best parts of single table design and GraphQL at the same time, you want to make sure you get back the full picture. So that's using GraphQL to make a query like this that will bring back details about the project and all the tasks relating to it. So a simple query that would enable that with DynamoDB would be to just make a query that requests that looks for the project ID on the table partition key. So looking at our table again, we would get in our results these three items in an array. We would then use a response mapping template to iterate over that data and aggregate it into the necessary JSON structure to return to the API. So this is what a VTL template that performs that logic would look like. You iterate over the results and you use the type prefix of each item to determine where it fits into that structure, and then you create that object and send it back to the API. And if you want to test VTL templates to find out if what you're doing will really work when you deploy it, I've created a blog that you can check out. It's on the Mechanical Rock blog. It's called Ensuring Resolvers Aren't Rejected, and I've put the link in the slide deck. So what about many-to-many relationships? Many-to-many relationships are always hard to deal with and should generally be avoided, but that's not always a viable solution. With DynamoDB, there are a few ways you can go about this, but one that I will talk about makes this problem much easier to solve. So for a project to get completed, it needs to have users assigned to it to get the work done. So users can be assigned to many projects, and a project can have many users assigned to it. And so to model this relationship, we will use what's called a reverse or an inverted index. Now, to create that index, we'll have to create a GSI where our current table sort key is the new partition key for the GSI, and the existing table partition key is the sort key for the new GSI. So you can see that's why it's called the reverse index. And using this index, we will be able to find all of the users that are assigned to a single project and all of the projects that a user is assigned to. To avoid duplicating data for each user and each project, we will only store the ID reference in the sort key column for each user on each project. This means that we will need at least two queries when retrieving the finer details of each side of the relationship. Fortunately enough for us, this is easily achieved with Appsync and pipeline resolvers. With a pipeline resolver, we'd be able to submit an initial request with a VTL template to find all the users assigned to a particular project. We'd then be able to follow that up with a subsequent VTL request template that requests all of those users' details with a batch get item request. So the image in this slide just gives you an idea of what the reverse index will look like from the other side and what sorts of queries you can make with that index. And to come up with these images, I've actually just used the DynamoDB Workbench client that you can download. So having just witnessed the best parts about single table design, you can see that it's a great fit for modeling data in DynamoDB, especially in applications where you have clear relationships between entities. So given that Regia is a project-centric app, we could use the project partition to retrieve all of the information about a single project at once, or if we wanted to, we have the flexibility to break it up into many smaller and potentially more meaningful queries depending on the application requirements. So what if you wanted to do a hybrid and mix up multi-table design and single table design in the same application? Well, there are a few use cases where you'd want to do that. So one of those use cases might be that you have a requirement for Regia to track the changes that a task goes through over time. You might be using DynamoDB streams, as it's a good way to keep track of data as it changes in the system. But if you have really high throughput of changes, and you don't want to create a loop where each time a record is updated and triggers the stream, a resulting record is written back to the same table, ending in the stream being triggered again once more, you might find it more beneficial to pipe this record through to a different table. And the reason that's beneficial is because if you were creating a loop, you would end up with extra compute costs for each unnecessary Lambda invocation. You would have more logs to filter through, and that of course would make it difficult to debug. And of course, you would be complicating your stream logic with a bunch of, in this case, unnecessary if statements. And putting this data into a different table might be really great if you were to use something like a k-sortable UUID for a sort key. You could then create a versions table with the task ID as the partition key and the new k-sortable UUID as the sort key, which would then enable you to retrieve an ordered list of all the task updates or versions over time. And so with those new components added into our system, this is what the new architecture would look like. You've got your DynamoDB updates going into your stream, which then update your new versions table. And so here we can actually have Appsync query the existing core table or the new versions table for the task versions. And so this is what that new versions table would look like. You can see in the middle column, you've got the new sorted IDs in ascending order that would retrieve the versions as they've happened over time. So another use case for multi-table design is that you might have a separate team who wants to build a service with its own API for a bespoke client application. In this case, the data probably has a different context or life cycle to the existing Regia data. It might be a service that wants to aggregate and graph project metrics to display for management's perusal, because who doesn't like a good burn-up chart, right? Naturally, this data would reside in its own table as it's part of its own API. However, that's not to say that it can't be constructed as a reusable microservice. The team might choose to use Appsync or API Gateway. However, this isn't important as you do have options in this regard. If you want to get all the benefits of Apollo and GraphQL, you don't want to manage multiple Apollo clients in the same application, because this can easily become really complicated when you have to deal with 2 caches and 2 clients. What you want to be doing is stitching your schemas together if you're using Appsync, or create queries and mutations that map to the new API. And to do this, you want to use Appsync resolvers that use VTL templates to access your new API with your existing API. With an additional service stitched into your schema, your new architecture would probably look something like what we have in this slide here. And if you do this correctly, your application should only have one Apollo client and one API to care about. And this actually will simplify things a lot from a client application development perspective. And so finally, in summary, we can see what we learned about single table design is that it's great for grouping related data together. It enables you to retrieve related data with a single query, whilst also exposing the flexibility to make smaller, more decisive queries as well. You only have to monitor one table as opposed to monitoring many tables. And using single table design also forces you to consider all your access patterns up front, which means you probably then also have a better grasp of your application requirements. Multi-table design is generally good for separating your data according to separate concerns. With multi-table design, you also get more indexes, you get more streams, which means it's more forgiving for newcomers as well. Thank you to all the organizers of this event, and I hope you enjoyed this talk. Cheers.